Hello everyone, my name is Tanner Bohn. I am a PhD student at Western University. The work I'm presenting today is titled A Deeper Look at Bongard Problems, a collaboration between Xinyu, myself, and our supervisor, Dr. Charles Ling. Here is a Bongard problem. Our task is to look at these 12 tiles, 6 on the left, 6 on the right, and try and come up with a rule which clearly classifies those on the left from those on the right. In this case, there's a rather simple rule of large figures on the left and small figures on the right. However, there are hundreds of Bongard problems, each of which requires its own unique rule, and they come in a wide range of difficulties. To consistently solve Bongard problems requires at least 3 skills which are central to human intelligence. The first is divergent thinking, where we must consider many different features that maybe we don't even know in advance. It requires abstraction, so features based on simpler features, based on simpler features. As a simple example, we can look at the spiral BP here, where we need to compose pixels into edges, edges into curves, curves into spirals, and then recognize the direction of the spiral. In this third example, even more abstraction is required, but I will leave that to you to solve. Third, solving BPs requires few-shot learning. We only have 12 tiles to learn a rule. This is in stark contrast to the thousands or millions of examples which is common in image classification. To provide a little bit of context, Bongard problems were created in the 1960s by Mikhail Bongard to demonstrate that the pattern recognition techniques of the day are kind of terrible. They were later studied by David Hofstadter and his grad student Harry Foundalis around 2006, and this resulted in the Fayeko cognitive architecture. Since then, there have been very few attempts with modern AI and machine learning. So, how do we solve Bongard problems? There are 3 different skills we know a solver should possess. So for few-shot learning, using pre-trained feature extractors is relatively common. Second, we know that CNNs tend to learn increasingly abstract features in subsequent layers. And to achieve some version of divergent thinking, we can simply consider many features. So we can consider the activation for every kernel at every layer of the CNN. Next, we'll look at how we actually put these ideas together to solve Bongard problems. The first step is to generate a whole lot of random shapes and pre-train a CNN to classify those shapes. Next, when we have an actual BP that we want to solve or find a rule for, we can take those 12 tiles, generate a feature vector for each of them, where each dimension of the feature vector corresponds to a particular filter in the CNN. And then we can train a classifier on those 12 feature vectors, 6 negative and 6 positive. Finally, when we have a new tile that we would like to classify, we can generate the feature vector for it, feed it into the classifier, and predict the side. If we have a BP solver, how do we actually evaluate it? We've identified 3 different properties that we believe a BP solver should have. The first is validity. That is, does it correctly classify the original 12 tiles. So we train a classifier on the 12 tiles, and we consider it valid if it is again able to classify those 12 tiles. Second feature is robustness. So given a rule which correctly classifies the original 12 tiles, how often does it also classify additional tiles which follow the intended rule? The third feature is simplicity. Ideally, the solver should produce rules which are interpretable to humans. Unfortunately, this is quite difficult to rigorously define. So in this work, we will simply inspect the activation maps and try and understand what they're doing. To give an example of how there can be many different valid solutions to a BP, we provide this example. So a rule which is both simple and robust, which a human might come up with, is polygons on the left and curvilinear shapes on the right. A rule which a machine may come up with, or a rule which is easiest for a machine to come up with, could be based on the values of individual pixels. And then there are also combinations of complex and robust, and fragile and simple. So for any given problem, there are many valid solutions. So now we'll look at our experimental setup. So there are 4 main decisions we need to make for our experiments. First, for the CNN architecture, since we don't particularly care about how the architecture itself affects results, maybe later work, we use a relatively simple architecture with the same layer repeated 4 times, 3x3 convolutions, 64 of them, with ReLU activation and 2x2 max pooling, and then a softmax output. For pre-training, we consider 5 different sets of shapes, each of which contains all the previous sets. So these shapes range from just single segmented lines, dots, or curves, all the way up to equilateral and non-equilateral polygons. For the actual classifier, we considered 2 simple options. We consider single feature selection. So the classifier needs to choose just one dimension of the feature vectors. Second classifier is logistic regression. So it can come up with a weighting over the entire feature vector. For the actual feature sources, we consider different subsets of the CNN layers. So this ranges from just the output layer all the way to the output plus all of the convolutional layers. So now look at our experimental results. We include the 2 tables here, but we'll jump straight into the main observations. First, in terms of the pre-training complexity, we find that higher complexity tends to translate to higher validity. And this is especially true for the logistic regression model. This may be true partly due to the fact that with higher pre-training complexity, there are more shape classes, therefore the output dimensions are higher. In terms of the classifier type, we find that while logistic regression tends to have higher validity, using a single feature tends to produce more robust rules. So this means that even though fewer BPs have valid solutions. Of those that do, the rule extends to the test samples more often. In terms of feature sources, of course we find that more layers translates to higher validity. However, there's no clear effect on robustness. And this may be due to the features in the later layers already producing the most robust rules. Finally, although it's difficult to draw direct comparisons with previous works due to differences in methodology, our approach is able to get around 30% validity using a single feature, whereas previous approaches on the same set of problems get around 7.5 or 19% validity. So to visualize the rules that our approach learns, we'll consider single features which produce valid solutions, and we'll visualize their activation maps and try and make sense of them. So sometimes these rules are quite easy to interpret. For example, in BP number 21, we see that on the left, it highlights all of the small shapes. And indeed, the rule for this problem is on the left there are small shapes, and on the right there are no small shapes. Sometimes the rule it learns is interpretable, but it's not actually the intended rule. For example, in BP number 183, the intended rule is same curvature in the middle versus a change in curvature. However, we can see that the rule learned here is more like, on the right-hand side, there are large empty spaces near corners, whereas on the left-hand side, that is not quite as true. However, the rules are not always so easy to interpret, nor is it always clear what should even ideally be highlighted. For example, in BP number 8, the rule is on the left-hand side, the shapes on the right side, and on the right side, the shapes are on the left side. Now, what should be highlighted? If it highlights just the shapes themselves, that doesn't provide us much useful information. Perhaps it could highlight the entire side that the shape is on. It's unclear what should be highlighted. So in conclusion, we find that Bongard problems appear to require skills central to human intelligence, making them quite interesting to solve with, or try and solve with, modern machine learning techniques. We recommend some intuitive metrics for evaluating BP solvers. And we propose an easily extendable approach for solving BPs with partial success. While there are many interesting directions for future work, two in particular are considering an active learning component to the problem so that an approach can iteratively narrow down hypotheses, as well as developing visualization tools better suited to these highly abstract patterns. All right, thank you. If you want to check out our data set, you can go here. And if you have any more questions or want to contact us, you can do so with these emails.